So we're going to begin talking about slender members, which are all around us. The most common example is probably the beams that you've seen used to construct high-rises, but long, thin members that support forces, both point forces, distributed forces, are all around us. And they're very important. And as we dive in to think about the forces and the moments on these structures, we need some way of having a common language to speak and a convention. And our convention in 3 dimensions for the forces, here shown in green in the 3 coordinate directions at the end of a long beam, and then the 3 moments about those axes. And our convention is going to be forces are F, moments are M, with the subscripts being the first representing the face on which the forces are acting and the moments are about. And here the face is in the X direction because the normal to the face is in the X direction. So for what I've drawn here for this slender member at the end, the first subscript are all X's because this end face is perpendicular to the X direction. And then the second subscript denotes the direction that the force is acting, Fxx here. Y is up, so that's Fxy. Z is this way, so it's force Xz. Again, the force on the X face acting in the Z direction. The 3 moments have a similar convention. The first represents the face the moment is acting on, and moment XX is acting on this X face and in the X direction. And by in the X direction we mean by the right hand rule about the axis that's about which the moment is acting. So if I stick my thumb in the X direction, MXX will be this way. If on the X face I stick my thumb in the Y direction, MXY would be in that orientation, tending to swivel this beam that way. And then if I stick my thumb in the Z direction, the moment acts about this rotation for moment XZ, X face Z direction. Now, in order to simplify working problems, we're going to do most of our work in the 2D space. And so the convention gets reduced, because if we are looking down the Z-axis with the X-axis to the right and the Y-axis is up, and we're only interested in the 2 forces and 1 moment about the plane of the board, then we're left with this at the end of a 2D slender member in the board. We're now, instead of worrying about the subscripts, since we only have 2 forces to worry about in 2D, the force is going to be in the axis down the length of the slender member, and this is Fxx in our 3D case. So this could be force sub x, but we're just going to leave the subscript off because we're going to call the force which is acting parallel to the surface shear. So this F is going to be our longitudinal force. V is going to be our shear force, because it tends to shear on that surface. And then the moment, there's only 1, and it's acting about the direction perpendicular to our 2D plane. And we're going to give it a subscript B because this is going to be a bending moment, and it's going to tend to make our slender member, our beam, either smile or frown as we tend to bend it. So we're just going to call this the bending moment. So primarily we're dealing with these three quantities that will exist at any point along the beam. Another convention to be aware of is this force is acting in the right direction. So it seems normal that we would call it a positive force, and indeed we do. The shear is acting in the positive y direction, so we would call that a positive shear force. Seems reasonable. And then this bending moment by the right-hand rule is also positive. But what that means is to be in equilibrium, if we consider a free body, which is a section of our slender member, in order to balance out a force in that direction, we of course would need a balancing force of F in this direction. And we don't want to say we have a positive force on one side, negative on another. In this beam, the force is going to be positive, something that in other jargon we call tension. That means that this force has to also represent a positive orientation. And the way we think about it is a force outward on our end is a positive tensile force. And on this side, this force is outward, balancing that one. So this too is a positive or tensile force. Likewise, shear up on this side would be balanced by shear over here. And so this too is a positive shear because it's acting in the negative direction on the negative face. And then finally, that moment would be balanced by a moment like this. And this too is positive. And so it is in the direction into the board to balance this one out of the board, and positive moments tend to, as we say, make our beam section smile. These are positive quantities, that orientation I've drawn. These are also positive orientation as I have drawn. So let's think of an example that simply teases out the concepts that we're getting after for thinking about, again, a long beam. It's going to be supported some ways, maybe by point supports, could be cantilevered off of a wall, subject to forces. Those forces could be, say, those point supports on the at the constraints. It could be forces of weights on the top that are applied at particular points, or maybe they're distributed along the beam. So we've got constraints to worry about, and we have loads to worry about that are typically point loads or distributed loads over a length of the beam. Here's a simple example of a beam, a slender member, and it is simply supported with a weight hanging on it. And if this beam has an overall length of L, we'll say this weight is hanging A units from the left side, B units from the right side. So let's pause for a moment and revisit this idea of how we draw our constraints. This one on the left with a little pointy triangle means I am pinning this beam at this point. The crosshatch means I'm pinning it to a surface which is rigid and not going to move. And the pin at the top is constrained such that it cannot move in the X direction and it cannot move in the Y direction, but it is free to rotate in this maybe smiling or frowning sense. So it can have an angle at this point, just like you would expect a real pin between two structures to allow one to rotate about the other. So this is a pin joint. The other side I've drawn a little differently. This is a roller. So just like you would imagine a rolling pin, I put that between the beam and my rigid surface. It constrains motion from not happening in the y direction or perpendicular to this surface, but the roller sense means I will allow motion in the x direction. And because, like a pin, there's nothing preventing an angle from happening there at the end, it allows rotation. So here, rotation is the only thing allowed, and here we permit rotation and a translation in the x direction, fixed in y, fixed in xy. Now sometimes you may see, for simple cases, that someone will have a pin at both sides. And if I pause for a minute and let you think about what that would mean physically, it would be saying, well, I'm not allowing any x or y displacement here. I'm not allowing any x and y displacement here. That would mean I'm not allowing any change in length for the beam or the slender member. And in real life, if we hang a weight W here, and there tends to be a deflection downward, well then the two ends of the beam are going to get a little closer to give us that length of displacement downward, and they will move closer together. If I fix them, I may generate a lot of force in the x direction, in this direction, to prevent that. One thing we're going to be talking about in this section of the textbook, though, is just about equilibrium. In a later chapter, we're going to get to the deflections of this beam. But in this video, in this lecture, we're only talking about equilibrium, so we're not going to worry too much about constraining things like this x displacement from happening, because that will be left for a more advanced treatment of, gee, how much would it tend to get shorter? But these are the boundary conditions on our beam. And the only reason we want to restrain it in the x direction one place at all is to stop it from zipping off into space. I think if you saw an example with two rollers, you might just give the person drawing the picture the benefit of the doubt that he or she meant to not have the beam rolling across the whiteboard and off the edge. So W is going to put what we would model as a point force on this beam at this location. So our question before us is, what forces and what moments is this beam subject to by hanging this weight W from that location? So step number one is going to be to determine what are the reactions, and by reactions I mean the forces and moments at the constraints and to get at this, we are going to make use of overall equilibrium. So what do I mean by that? I'm going to mean that we're going to replace our constraints here with the unknown forces, and I'm going to draw these in the positive direction. So we're going to call this the reaction at point A, and the reaction at point B. And then, although it is somewhat trivial, we're going to put at this point a point mode W. So we're going to balance all of these out, and right off we can see, well, RA plus RB is going to equal W because of some of the forces in the y direction has to sum to 0. But we've got two equations, two unknowns and only one equation. We need another one. The other equation is going to be a judicious choice of our moment, just like we did in the last chapter, in order to get at what these values are. So let's write those equations. So finding the reactions, we see that RA plus RB. And now sometimes people are thrown off by what direction do I want to write these things. And just to show you that it doesn't matter if you get these things wrong, why don't we can write W as being upward, knowing that the value is going to be a negative magnitude of W. So this would be plus W all equals 0. And this is taking the sum of the forces in the y direction equals 0. So we compute that RA is equal to the opposite of W minus RB. Now the sum of the moments coming out of the board, we're going to call those bending moments, has to be equal to 0. So we need to pick what's a good place to take the moment about. Why don't we just take it about this point here at A. So instead of using bending and get confused with point B, we'll just say about A. So the force at A, due to the reaction, operates through that force. So it has no contribution to bending. And then we've got a positive AW, which is the lever arm times the perpendicular distance to the force and its magnitude, plus, again, positive is RB at an angle L. LRB is equal to 0, so we can solve for RB is equal to the opposite of AW over L, and then just plugging this back in here, we get RA is equal to minus W minus RB, which is plus AW over L. So using overall equilibrium, we now have quantities for RA and RB, and W presumably is given, but that really doesn't tell us how much force and a bending moment is having to be borne by this beam from one side to the other. which part of this beam is most likely to fail if we were to load it this way? And that part we really need to get at. So we need to generalize and come up with a way of computing at any arbitrary point. And let's just say at some point x from this end. So at just some arbitrary point, what are the forces acting here? What's the bending moment acting there? So what we're going to do is come up with a method for consistently doing that. And in the textbook, there are two ways of coming up with this computation of the distribution of forces and bending moments down the beam, that we either do the intuitive, cut the beam, write equilibrium at an arbitrary point, write our equation. The second way is to use a technique called singularity functions. And now singularity functions are very interesting, and once you get the idea, the physical feel for how this goes, the singularity functions are expedient in that they allow you to get to a final answer faster. However, I think we miss something about internalizing how this goes when we jump straight to that. So we're going to spend some time making sure you're comfortable with the procedure for cutting the beam at the point of interest and then just applying equilibrium. So for us in this case, we are asking ourselves if we are to cut the beam at some point x, we're literally going to lop off the part to the right of that and replace the effect of the missing part of the beam on the remaining part of the beam as an unknown force and moment. So here we're going to make our cut right there. So what we're left with is a bit of a beam with RA acting on this side and an unknown shear and an unknown bending moment at this unknown point X. I didn't bother to write F because there are no forces in the X direction to sum up. So I know that there's no force acting in the X direction because then we would be violating equilibrium. So we're left with this shear direction force to counter RA and this moment. And if we write the equation for this, then we've got summing the forces in the y direction means that RA plus Vx is going to be equal to 0, which tells us that the shear at any point X is equal to the opposite of RA, which means it's equal to W minus AW over L. All right, so we know what the shear is acting between those 2 points. One thing that's interesting about this cut the beam business is we realize that we will get a different equilibrium equation if our arbitrary point is to the right of where W is applied. that leaves us with having to remember that we have to make as many cuts as we have loading events starting and stopping down the length of the beam. So here we've got nothing happening in here, so we just need one arbitrary place x. But when we get to the right of where W is applied, now we're going to need to write a second equation for cutting the beam out here. So this is the equation for Vx that applies between the left end and where W is applied. So what if we cut our beam instead of there? We now make a cut through this part, which means X is all the way out here. And now what we do when we write equilibrium for lopping off everything to the right of our point is we end up getting something longer here. W is applied at this point, and then at this we have an unknown V at point X, and then we have our unknown moment about X as well. And I forgot to write the X equation that went along with this part. And we should take care of that. So the picture looks the same, getting ahead of myself, but we don't have the W acting with our cut here, just a longer picture. So what is this moment then? So if we sum the moments at point, or to compute this, we'll see. Okay, due to a technical glitch, my lecture continued even though the camera quit recording, and I made it this far through a description that I think you'll just have to trust me was brilliant. I'll recap now instead of trying to reconstitute where I was. And I think we were here figuring out what equation would give us the shear and moment description from the left end of our beam up to the application of the force W. And just to make the math more concise, the reaction at A that I believe we determined was this value, we can reduce that to being W over BL in magnitude. So we summed the forces. I think we got this far. We were on the moment equation. So in looking at this part, cutting the beam anywhere between the left end and the application of W, then we didn't have this. We were solving for the sum of the forces in the y direction, which is RA, plus that unknown V at the end. And then the moment equation sums to 0. If we sum about this point, the only two contributions are Vx and Mx. And then to look at the length of the beam between W and R, we take the exact same approach, but now we know that there is a W for x's in between the point of application of the weight all the way to the end. And that gave us a balance for the sum of forces in the y direction of this term, and this term. And then the moments, the contribution about A is due to W, Vx and Mx. And we were able to derive equations for those two. And now we are going to plot what are called shear and moment diagrams for this beam. And this is a very common technique. And if you take the fundamentals of engineering exam, you will need to do shear and moment diagrams. Here we plot the shear from the left end to the right end. And sure enough, if we're thinking about the shear in the beam, we need a reaction as we're moving our way across at this end that's opposite to RA. When we get to W, then we jump up by a magnitude of W, and in this section we need a force of magnitude AW over L to counteract the sum of these two forces. So this is our shear diagram that tells us that shear force. And where's the worst part? Well, the worst magnitude is just to the right of application of W. But of course, if we're truly at a point load, this thing is going to fail right where W is pushing, and the real life area over which the force is distributed is very important. For the moment diagram, now from here to here, we're plotting out this relationship, and the moment increases linearly until we get to the point of application. Then from this side, we apply this equation from this point over. It is linear in x2. A verification that this is right. We had no moments at the end of the original beam, you'll remember. Nothing there restricted a rotation from occurring. So there was no moments counteracting the motion at the end. So at 0, the maximum moment is where W is applied. So this area of the beam is definitely the highest loaded point with shear and the maximum moment in the beam, where W, of course, is a negative force pulling downward. And that's shear and moment diagrams. And to preview looking ahead, we're going to use these values in order to determine the stresses in the beam, which is going to depend upon the geometry of the beam, whether it's an I-beam, square beam, circular section, and then we'll also need to know if that stress is too much for the beam. So we'll begin to talk about the material the beam is made out of to know what it can withstand. So that is an introduction. We'll pick up in the next lecture more about shear and moment diagrams with another example. And trying to remember what else I would have covered in the missing part. I think that's it.